In this video, we're going to be talking about interpreting center and variability, Chebyshevs Rule, the Empirical Rule, and zScores. So interpreting center and variability. Chebyshevs Rule is the percentage of observations that are within k, standard deviations of the mean. And it's saying that it's at least 100 times 1 minus 1 over k squared percent, where k is greater than or equal to 1. So if k equals 2, then at least 75% of the observations are within 2 standard deviations of the mean. Notice here that we took the k value and replaced it with the number 2 since we had said let k equal 2. This rule can be used with any distribution, no matter its shape. So let's take a look for the sample. We have a sample of families with one preschool child. It was reported that the mean child care per week was approximately 36 hours with a standard deviation of approximately 12 hours. Now, using Chebyshevs rule, at least 75% of the sample of observers must be between 12 and 60 hours, because that's within 2 standard deviations of the mean. So at most, what percent of the observations are greater than 72 hours? At least 89% of the observations are between 0 and 72 hours, since time can't be negative. So at most, 11% of the observations are above 72 hours. Let's talk a little bit about area. So we're going to input the following command into a graphing calculator in order to graph a normal curve with a mean of 20 and a standard deviation of 3. So what we're going to do is we are going to, on our calculator, go to our y equals. Then we're going to go to our second distributions, which is our vars menu. Then we're going to select normal PDF. So option number 1. Here we're going to have an x value of x. So we'll plug in an x. We'll have a mean value of 20. And we're told that the standard deviation is 3. Then we'll come down here to where it says paste and hit enter, and that will put in our function into our y1. Now it's also given us a window to use, so for our window we'll go to window, and we're going to have an x minimum of 10 and a maximum of 30. So we'll enter that in, 10 and 30. And then we'll have a y minimum, it says, of 0, and a y maximum of 0.2. We'll change that resolution to scale to a 1. And it says, next, we're going to graph it. So we're going to go ahead and hit graph. And here we see our curve. Then it says to use the to use the command second trace. So we're going to do second and trace, and that's going to calculate. And we're going to choose option number 7 because that's going to help us to find the area under the curve. So we're going to go ahead and enter on option number 7. And we're going to do that a couple different times as we look here at our lower limits and upper limits. So right now it's asking us for our lower limit, so we're just going to arrow over to 17. And when we get to 17 as close as we can, so 16.96 is a lot closer than 17.12. So we'll take that and we're going to hit enter for our lower bound. Then we're going to arrow over to our upper bound of 23. And when we get there, we're going to hit enter. And it's going to tell us the area of our graph, which in this case is 0.68755531, and we're going to round that to 3 decimal places. We're then going to repeat this process again with a different lower limit and a different upper limit. So we'll go second trace to get to our calculate menu, choose option number 7, and find a new lower bound of 14 and a new upper bound of 26. And here we see that we have an area of 0.9566, so 0.957. You tried the third one on your own. So go ahead and push pause, and then when you're done, push play, and let's see if you're right. So here we have a lower limit of 11, and we have an upper limit of 29. And here we see that our area is 0.9950. Let's go through another example. So we're going to go ahead again and go to our y1, so go into y equals, and we're going to change our normal PDF. So we're still going to have an x of x, but this time our mean is 50, and our standard deviation is 5. So notice that because I already had that in my y1, I didn't need to go through that whole same process of going to the distribution menu. I was just able to change those values. So now I just need to go into my window and change my window so that I have a minimum of 30 and a maximum of 70 for my x values. And for my y's, I have a minimum of 0 and a maximum of 0.1. And then when I graph that, here I see a slightly different curve. So we're going to find the area under the curve for the following. So I'm going to go ahead and have you do these ones on your own. So go ahead and push pause, and then when you're done, push play, and let's see if you got the correct areas here. So you should have gotten the areas 0.682, 0.954, and 0.997. What pattern do you notice that we've seen in the last two examples? Are those pretty similar? Let's talk a little bit about interpreting center and variability. The empirical rule. The empirical rule can only be used with distributions that are mound or normal shaped, which is why Chebyshevs is nice because it will work with any distribution. But if our distribution is mound or normal shaped, the empirical rule is going to give us a much more accurate answer here. So approximately 68% of the observations are within one standard deviation of the mean. And approximately 95% of the observations are within 2 standard deviations of the mean. And approximately 99.7% of the observations are within 3 standard deviations of the mean. Let's look at an example. So the height of male students at PWSH is approximately normally distributed, with a mean of 71 inches and a standard deviation of 2.5 inches. So because we have a normally distributed or an approximately normally distribution, we want to use the empirical rule. So what percent of the male students are shorter than 66 inches? So here we're thinking of a normal distribution. So if we were to draw our normal distribution, here we would see that we have a mean of 71 inches, and that each standard deviation would be 2.5 away. So then we'd have 73.5, then another standard deviation of 2.5, would give us a value of 76. And then another standard deviation of 2.5 would give us a 78.5. And then going in the other direction, so still a distance of 2.5 away, we would have 68.5, and then another standard deviation of 2.5 would give us a 66, and then another standard deviation of 2.5 would give us a value of 63.5. And so here it's asking us what percent of the male students are shorter than 66 inches. And so if we look at our graph here, we're going to see that 66 is going to be right here. And we want to know what's on this side. Well, remember that from here over is worth 50% of the information. Then between this spot right here, so from right here to here, that's worth 34%. And then from here to here, that's going to be worth 13.5%. And so we're going to go ahead and we're going to add those values up. So we're going to add our 13.5%. We're going to add our 34%, and we're going to add that 50% to get our answer. And that's just one way. There's lots of different ways that we can add or subtract. For example, we also could have taken 100 and minused just this portion, and that would have worked also. So if we take 13.5 and we add that to 34 and then add that to 50, we're going to see that that comes out to 97.5% of the male students are shorter. Oh, right, excuse me. That's who is larger, right? Who is taller, because we just did this side. So we now want to take 100 and subtract that value, and that's going to tell us how many are shorter. So if we take 100 and subtract our 97.5, we'll see that 2.5% of male students are shorter than 66 inches. Now the next question that we're asked is which percent of the male students are taller than 73.5 inches? And so here we're going to come up to this spot right here, and now we want to know what are the numbers on this side. So this value is also worth 34%, and so this portion is worth 50% because it's on this half of the mean. So we're able to take our 50% and add the 34% to it to get 84%. Then we're going to take 100% and subtract the 84% from that. And when we do that, we're going to see that we have a value of 16%. So 16% of the male students are shorter than the 66 inches. And our final question here is it wants to know what percent of the male students are between 66 and 73.5 inches. So between 66 and 73.5 is going to be right here. So we want to know what is this percent? Right there. And so what we're going to need to do to find that is take our 13.5 and add that to our 34 and our 34, or we could have just called that 68 since it's the one standard deviation away from both sides. And when we add those three numbers together, we come up with a value of 81.5. So that tells us that 81.5% of the male population, or male students, are going to be between the heights of 66 and 73.5 inches. So let's go ahead and let's talk about measures of relative standing, the z-score. A z-score tells us how many standard deviations the value is from the mean. And our equation is to take the value minus the mean and divide that by our standard deviation. This is one example of a standardized score. So what do the following z-scores mean? If I have negative 2.3, that means that I'm 2.3 standard deviations below the mean because it was a negative z-score. 1.8 means 1.8 standard deviations above the mean. So what do you think negative 4.3 would mean as a z-score? That's right. It means 4.3 standard deviations below the mean. Let's take a look at an example. So Sally is taking 2 different math achievement tests with different means and standard deviations. The mean score on test A was 56 with a standard deviation of 3.5, while the mean score on test B was 65 with a standard deviation of 2.8. Sally scored a 62 on test A and a 69 on test B. On which test did Sally score the best? Let's take a look at the z-scores here. So for the test A, we have 62 minus 56 over 3.5. So again, we have Sally's score minus the mean divided by the standard deviation. And we come up with a z-score of 1.714. Let's look at the z-test for test B. So we'll take our 69 that Sally got, subtract the mean of 65, and divide it by the standard deviation of 2.8. And that gives us a 1.429. So Sally did better on test A. Let's talk a little bit about percentiles. Now, a percentile is a value in the data set where R% of the observations fall at or below that value. So notice here, we say that this is the 90th percentile because 90% of our data is at or below that point. For example, in addition to weight and length, head circumference is another measure of health in newborn babies. The National Center for Health Statistics reported the following summary values for head circumference in centimeters at birth for boys. What percent of newborn boys had head circumferences greater than 37.0 centimeters? So what percent of newborn boys had head circumferences greater than 37 centimeters? Well, if we look right here, we're going to see that that's the 75th percentile is at 37. So if we want to know what was greater than 37, we want to know this area here. And so if we take 100 and minus 75, we see that that leaves us with 25% of the data left. So we should have about 25%. Then it says 10% of newborn babies have head circumferences bigger than what value? What do you think that the answer might be here? Well, if we want 10% of newborn babies to have a bigger than what value, then that means we're looking for just 10%. So we don't want to use this because we're showing that from 10 up. So our answer is not going to be 33.2. But instead, where do we have 10% left? And the answer is right here. This represents only 10% of our data. And so we can say that a head circumference of 38.2 centimeters would be our answer here. Now we can tell that the head circumference distribution for newborn boys is not symmetric because the 5th percentile is 3.6 centimeters below the median, right? That's not very far below our median. of 35.8. Whereas the 95th percentile right here, that's only 2.8 centimeters above the median. So this is going to suggest to us that the bottom part of the distribution kind of stretches out more than the top part of the distribution. So it's going to be a little bit more negatively skewed and might look something like this. So notice here that at this spot, we're at that 5th percentile, and here we're at the 95th percentile. And this is our median. And so here we see that that tail on the left is stretched out a little bit more than that on the right, giving us that negatively skewed distribution.